Where are neuromorphic devices currently? Not just physically, but where are they in terms of their progression as a technology? Hey everyone, and welcome to All Things Neuro. Today, I'll be discussing examples of neuromorphic devices that are being used to solve real-world problems and the maturity within the spaces they occupy. The application of neuromorphic principles can be quite broad. Some people may include software algorithms like AlphaGo, which were designed using learning principles derived from neuroscience. But in this video, and for much of this series, we'll be focusing on neuromorphic hardware that is analog, digital, or a combination. Okay, so before we get into where neuromorphic devices are currently being used, it might help to have an appreciation for what neuromorphic devices bring to the table. First off, these devices use very low power. This is beneficial in many applications where regular access to power supplies or batteries is limited, like an implanted medical device or a remote scientific instrument. Another benefit is that they can output better quality signals. This may be measured in terms of signal-to-noise ratios, sensitivity, and other similar metrics. If these terms are unfamiliar to you, you can imagine this as the difference between talking to your friend Alexa in a noisy bar and talking to Alexa in a noisy bar. One of them may have trouble understanding you right now. And lastly, the third benefit I'll introduce is the ability for learning that does not require the explicit computation of features or statistics. Neuromorphic devices with learning circuitry can adapt to changes in their environment without the need for special software instructions or interventions from human operators telling it how to adapt to these new inputs it receives. So, where can we use these benefits of lower power, better quality outputs, learning, and adaptation? Well, the short answer is everywhere. However, at present, they haven't made it into everywhere just yet. The technology, although promising, is still maturing. But I've picked 4 areas where neuromorphic devices have applications worth discussing. These are applications in medicine, small and large-scale compute, industry, and scientific inquiry. So first up, we have medical applications. Within medicine, there is a subcategory of devices called neuroprosthetics. Retinal implants fall into this category. However, only a few implementations use neuromorphic design. One particular design, created by Alan and Vincent Chow, is an artificial silicon retina, or ASR chip, that uses a photodiode electrode array to convert light into currents. The specific details of the chip are outlined in their 2004 paper. In it, they describe the microchip, its clinical application, and the clinical success recorded from patients in the trial. The chip itself is 2 millimeters in diameter and 25 micrometers in thickness. It's also equipped with 5,000 microphotodiodes, each of which is connected to a microelectrode that stimulates surviving nerve cells in the patient's retina. Remarkably, the total device is powered by incident light, with generated output currents ranging from nanoamps to microamps, depending on the strength of the light source. The photodiode array replaces the function of the damaged photoreceptors due to disorders such as retinitis pigmentosa. Biological photoreceptors themselves produce a graded voltage signal. However, the ASR chip is still able to communicate with existing nerve cells using graded currents to mimic normal cell behavior. The placement of the ASR chip in the direction of the stimulating current is such that it is hyperpolarizing in light and depolarizing in darkness, just as we would expect from healthy photoreceptors. The ASR chip allows patients to regain some visual perception in the form of brightness, color, movement, shape, and other object features. The results, however, are subjective and vary quite a bit. The approach taken by the ASR design has many advantages over other retinal prosthetic solutions, which typically use CMOS cameras to generate signals for the retina to receive. Foremost, there are no external power or processing requirements. This substantially lowers the complexity observed by patients to operate and maintain the prosthetic. This also means that there are no additional surgical steps to route wires from the eye through the skull, or transceiver coils to place. There are no batteries to change or external hardware to carry in order to perform processing. And there is no additional eye or headwear to use for mounting cameras. One takeaway I've noted for myself is that the simplicity of the neuromorphic approach allows for a higher density of photodiodes and stimulating electrodes. These two components are ultimately what allow patients to regain visual perception. Other solutions must instead reserve real estate for auxiliary hardware like transmitting coils. However, a notable drawback is that there must be enough light for the chip to power itself before it can start responding to the light. So even if there is seemingly enough light for the photodiodes to start responding, the ASR chip won't have enough power to generate any signals. More recently, another neuromorphic approach to restoring vision loss due to things like retinitis pigmentosa was explored in 2019 by the company GenSight Biologics. Here, researchers and engineers created a novel approach to existing methods that use light signals transmitted from a camera. Rather than using an implant to stimulate retinal neurons, the team leveraged an optogenetic technique that is typically used by researchers for investigations rather than clinicians for treatment. Specific light-sensitive genes were isolated from algae and placed into a viral vector. The viral vector was then introduced into the patient's retinal cells through an in vitro injection. This process enables a light-sensitive protein called channel rhodopsin to be expressed in the retinal cell membranes. Once retinal cells have taken up the gene and begin producing channel rhodopsin, light coming in through the eye causes the cells to depolarize and begin signaling information to the brain once more. At this point, a patient would be able to receive sensation to light under the right conditions, which are provided with the help of a neuromorphic camera. But first, let's take a look at a visual scene as someone with normal sight might see it. A traditional image sensor would constantly bombard the cells with light across the entire visual field, making it harder to resolve object details. This is why solutions with frame-based cameras require additional external hardware called visual processing units, or VPUs, to compensate. A neuromorphic camera, on the other hand, communicates changes in light intensities as they happen, and transmit those changes to the modified retinal cells. This type of information is more akin to what is produced in healthy retinal cells. The image is then projected onto the patient's eye through a headset. Another benefit of the neuromorphic camera is its high dynamic range, which is similar to that of human vision, and 1,000 times greater than a standard camera. This allows it to operate in a wide variety of light conditions and still produce quality output for stimulating the patient's retina. There are many other applications of neuroscience in medicine. However, many of them only exist in lab settings or have just been proposed as viable avenues for future development. If you are interested in learning more about where neuromorphics can be applied in medicine, a great review paper was published in 2023 by Khaled, Aboumerhi, and others in the Journal of Neural Engineering. Now, let's move on to some applications of neuromorphic computing. There is overlap here with many fields, including medicine, which we just covered. However, in this section, we are more interested in using signals for inferencing rather than producing them. Neuromorphic compute typically involves a collection of individual neural elements modeled in hardware. These silicon neurons, as they're called, are then connected in a manner that is optimized for the task at hand. Most of the important communication within these devices occurs with event data called spikes. As spikes pass through these chips, learning algorithms modify and store the states of the neural elements and the connections that correspond to the input state. If no data is present, the neural elements are quiet and consume little to no power. If the right data is present, it will trigger spiking activity in the neurons associated with the input. This makes neuromorphic compute hardware ideal for classification and inferencing tasks, where performance metrics such as speed, robustness, and accuracy are all desired at low power. They also happen to be the same characteristics desired in many edge computing applications, such as keyword spotting. Keyword spotting is important in many voice-assisted technologies. The keywords are typically processed on the edge, allowing the device to perform certain actions locally before connecting to cloud infrastructure, should they need exist. Products that are directly connected to a power grid may not care that its hardware is using more power and compute resources to process keywords than, say, a neuromorphic solution. But for products like drones and battery-powered cars, latency and the amount of power being used become relevant factors in the design. The neuromorphic approach to keyword spotting involves transforming the audio data into a set of features that is then converted into spike data. This is represented by the spike generator block in this diagram. The spike data is then sent to a neuromorphic compute chip for processing. If the keyword is recognized, the chip will output a unique state associated with that particular keyword. The utility and marketability of voice-assisted technology has made solutions that can accelerate the recognition of keywords like "Hey Alexa" or "Hey Siri" commercially desirable. Even though neuromorphic computing is still in its early stages of adoption into commercial products, applications like keyword spotting help provide credibility for neuromorphic compute as the de facto standard for future generations of inferencing solutions. Car companies like Mercedes and BMW have begun integrating neuromorphic chips into their fleets for keyword spotting and are exploring the use of the technology to process data from other sensors in their cars as well. One additional thing to note here is that as far as I can tell, the spike generation process is performed using traditional software and hardware pipelines. In the future, there should be an opportunity to use analog neuromorphic devices that convert audio signals into the appropriate spike patterns that directly communicate with neuromorphic compute hardware. Neuromorphic technology also has applications to larger scale compute tasks as well. Currently, many existing commercial problems like pattern recognition, optimizing network paths, autonomous vehicle control, along with data monitoring and threat prevention, are all solved using machine learning algorithms that sit atop traditional compute hardware. Hardware components like CPUs, GPUs, and purpose-built accelerators enable the processing necessary to handle the load and time constraints of the task. Large-scale neuromorphic compute can offer alternatives to many of these use cases, and they can do so while consuming several orders of magnitude less power. However, there is currently less commercial sale of neuromorphic hardware for these larger compute applications. This is in part due to the ongoing research in making the technology product ready, but also the competitive landscape that traditional approaches have created. These existing solutions work pretty well. Some other challenges involve updating existing infrastructure to work with spike data versus traditional analog or digital signals, refinement of the learning rules that enable recognition and inferencing tasks, and the current cost of development. However, if we look at the type of partnerships and contracts awarded for bringing these solutions to market, there is still an argument to be made about their success in this domain. Around the globe, 3 regional players have emerged with major government-funded efforts to develop large-scale neuromorphic chips: the US, Europe, and China. Each of these regions has developed a long-term roadmap in terms of funding and deliverables. In the US, DARPA funded the Synapse project, which started in 2008 and ran for 8 years. In Europe, the Human Brain Project, which was a 10-year effort that concluded in August of this year. And in China, there's an ongoing 15-year effort known as the China Brain Project that was launched in 2016, partly in response to the other aforementioned programs. In the private sector, there are program efforts here as well. The US-based company Intel created Loihi, and in Russia, there's Motiv NT with their Altai chip. Both companies have developed advanced neuromorphic technologies driven mostly from their own capital and fundraising efforts. There may be other government-funded projects that I'm unaware of, but these are the projects that are most often cited in the literature. In all of these efforts, there has been a significant military adoption of the technology in advance of any concerted commercial investment. For example, in the US, the Air Force Office of Scientific Research is exploring the use of neuromorphic compute to develop next-generation situational awareness technologies. Companies like IBM and their research division and HRL have been developing neuromorphic compute platforms under government contracts for nearly 2 decades. Other companies like Intel have more recently emerged with their own neuromorphic computing platforms, and their efforts have attracted the R&D interests of these government agencies as well. Although the success of these neuromorphic projects may be somewhat subjective in terms of them meeting their original goals, they undoubtedly continue to advance the field. Each of these efforts provides a milestone for the next. IBM began its journey with the Synapse project, which led to True North, which led to the development of the Air Force's Blue Raven supercomputer, and paved the way for the unveiling of the North Pole project earlier this year. In most of the applications discussed so far, the low-power aspect of neuromorphic devices has been an integral part of its adoption over existing solutions. However, in many industrial applications, power is not always a concern since equipment is typically connected to a reliable power grid. What is important, though, are things like robustness to changing conditions, accuracy in decision-making, low latency, and high-speed data capture. The fact that much of this can be done in a low-power solution is still appealing and can provide more flexibility in terms of how the solutions are built and deployed. Industrial and process monitoring are areas where neuromorphic vision sensors and small compute applications have found an early adoption. The rationale I have here is twofold. First, the visual inspection of events is a very natural way for humans to process information, and many vision systems have already been built using frame-based cameras. Neuromorphic vision helps extend existing frameworks and capabilities in a meaningful way. Secondly, for internal operations, companies typically have one customer, themselves. This lowers the risk of investing in new technology, so finding the best solution to a problem can be done carefully and in parallel with existing solutions until the process is ready to go live. Even as far back as 2014, I recall interviewing the owners of a company called Cognimem, who had customers using their hardware for a variety of vision tasks. One system developed was used to visually inspect and monitor the processing of fish. Now, to get a better sense of what applications the industry believes are market-ready today, I took a look at companies whose marketing included industrial applications. There, some use cases emerged that spread across 4 main objectives. These objectives include safety, quality, predictive maintenance, and productivity. And some of the use cases include things like motion analysis, high-speed counting, object tracking, and even fluid and plume monitoring. Today, most of these use cases are being supported by existing sensors and compute hardware. However, the landscape is rapidly changing. The addition of neuromorphic technology does not replace traditional infrastructure, but rather augments it through permeable layers of software and hardware interfaces. In future videos of this application series, I'll go into more details regarding specific solutions, along with the pros and cons of incorporating neuromorphic technology. Also, if you'd like to learn more about the use of event-based cameras in industrial applications, I provided a link to a vendor below. There you can find more information and visualizations of the event-based data in several use cases. Now, lastly, we come to scientific inquiry. There are many labs all across the world that are consuming neuromorphic devices as tools to aid in their own research or as a system to evaluate in order to improve on the enabling science. I personally find this aspect of neuromorphic applications most exciting, and the first example I'll discuss comes from the U.S. Air Force Research Laboratory's Falcon Neuro project. The project was developed in conjunction with the International Center for Neuromorphic Systems at Western Sydney University, with the purpose of facilitating continuous monitoring of atmospheric and terrestrial events from space. The result was the Falcon Neuro module, seen here, designed with two neuromorphic cameras, each using the Davis architecture, which enables the capture of both event-based data and image frame data simultaneously. Once completed, the module was delivered to the International Space Station on a resupply mission in December of 2021. It was then installed on the research module Columbus, and the cameras began operation the following month in January 2022. One camera is positioned downward, facing the Earth, while the other camera is forward-facing, looking outward towards space to capture the Earth's horizon, or the Earth's limb as it's also called. Views of the Earth from this angle reveal atmospheric layers. The cameras are assisting with multiple scientific and military objectives, including atmospheric research, spacecraft reentry monitoring, and advanced threat detection. In all of these applications, the fast microsecond response time of the neuromorphic camera pixels allow investigators to capture and analyze visual data in ways that has never been done before. Furthermore, the low power aspect of these devices make it a great fit for space deployment, where resources are precious and limited. Now, the last set of examples that I'll leave you with today all use neuromorphic devices within the neuroscience community itself. The same field of study that enables engineering of the technology is also perhaps its biggest beneficiary as well. Just as the patch clamp and in vivo microelectrode arrays revolutionized investigatory methods within neuroscience, many classes of neuromorphic devices are doing the same. Some devices are purpose-built and allow neuroscientists to test hypotheses about a variety of sensory systems like vision, olfaction, and audition. One interesting study I came across was by Niu and others in 2014. There, they used digital neuromorphic design on FPGAs to emulate mammalian muscle spindles. Once the model was validated against physiological recordings, the system could be probed and adjusted in a variety of ways, all while running at over 350 times faster than the original in vivo approach. Additional systems exist that provide neuromorphic resources at an even larger scale. Devices such as NeuroGrid, Spinnaker, and BrainScales allow for the testing of neural circuits and learning algorithms acquired through investigations into biological systems. These platforms enable researchers to emulate hundreds of thousands and even up to billions of interconnected neurons at a time. Although the actual scale pales in comparison to human brains, they are sufficient for studying the dynamics of specific brain circuits or detailed connectomes of smaller organisms, ranging from insects to cats. Now, technically, these devices represent a subset of neuromorphic compute systems, like the ones I discussed earlier. However, I don't want to conflate the use of these neuromorphic systems with the type of applications discussed in the large-scale compute segment. Here, these chips are being used to demonstrate complex behavior that can be matched with observed behavioral and physiological data from biology. A great example of this comes from Schreiber and colleagues. In their 2020 paper, they described the use of a neural circuit model to optimize route planning in a closed-loop system. The model itself is based on physiological data collected from foraging nocturnal bees, and it describes the neural pathways involved in their path integration. Path integration is the ability to derive a path from point A to B using points or routes not on the line AB. Its theory provides an explanation for how many insects navigate. Here we see a foraging bee, and its home location some distance away. Bees are remarkable for their ability to travel along unplanned routes in their search for food and then fly a direct route back home, regardless of the complexity in their journey. In the experiment, electrophysiological recordings were taken from the central complex of 160 bees while simulated movements were projected onto their eyes. Neurons encoding for visual compass sensing, optical flow, and the integration of speed and direction were then observed. Data from the neural recordings, along with an anatomical study of their connections, revealed networks sufficient for reproducing path integration behavior, both numerically and in closed-loop robotic simulations. Further mapping of the network onto neuromorphic hardware offers chances for enhanced study and experimentation. Rather than simulating behavior, spiking neural hardware allows for biological emulation. Visualizing these three steps simplifies systems and computational biology quite a bit. However, it does capture an important part of the scientific process, the path from discovery to validation. The ability to validate one's findings is often not trivial, and the methods chosen impact both the rigor needed to perform the validation as well as the level of confidence the community can derive from the work. In this particular example, an independent group of researchers were able to further validate the model using the BrainScale's neuromorphic system. Once the neuron parameters and the network topology of the model were mapped onto the hardware, experiments could be accelerated by up to 1,000 times their biological time equivalents. All neurons involved in the model could be monitored and analyzed together in real time. And spiking data from the hardware could be directly compared to physiological data collected from the bees. Now, in the original experiment, the investigators could only record from one neuron per bee at any given time, due to the small and delicate nature of the specimen. They validated the resulting model mainly through software simulations, where navigational performance was assessed. The research yielded some useful results. Work like this has enabled advances in drone operation, for example. However, the model does not embody the robustness of a fully functional bee. So, given the limitations of what is possible in wet lab experimentation, neuromorphic hardware can be used to iteratively refine the models through closed-loop experiments. The refinement process is similar to other validation methods. However, the main difference here is the emphasis on quantifying input-output relationships in real time. Providing inputs to the model invokes patterns of responses. Particular patterns within a response can then be used to control behavioral outputs, like steering a virtual bee in a particular direction. Experiments where the outputs continuously modify the system's inputs in a measurable way close the loop in the experimentation process and allow for meaningful correlations to be established between inputs, outputs, and the model. Now, the final act is to use this information to make adjustments to existing network models. To accomplish this, metrics are defined to compare against some type of goal behavior. Model parameters are then adjusted in a manner that brings the closed-loop behavior closer and closer to the original goal behavior. Models refined in this way can then be fed back as insight for neuroscientists, improving the pace of discovery. Other technologies can simulate biological systems, but the ability to emulate increasingly larger and more complete models of neural connections and their behavior is truly an amazing and unique aspect of neuromorphics, and its use is playing an important role in how neuroscience evolves. As we've seen, neuromorphic devices are being explored as solutions to a wide variety of problems, and the diversity of its application is really only limited by the creativity of those seeking possible solutions. However, in many commercial applications, the technology just isn't mature enough to replace existing ways of doing things. This lack of maturity spans many dimensions, from the development of the neuromorphic technology itself to the high development cost and lack of supporting infrastructure. There is even a shortage of engineers familiar enough with the technology to make industry changes widespread. So, as neuromorphics continue to evolve, they will likely first emerge in areas where traditional compute and sensing applications have failed, or in novel consumer products like toys and games, and as non-critical components within larger products. There will also likely be opportunities for non-commercial applications within military, medical, and technology research companies, where innovation is supported by financial investments, talent, and time.